So the term precise leveling is actually usually applied to the leveling practiced by the National Geodetic Survey, NGS. However, we're going to talk a little bit of how to make your leveling more precise, but we're not going to talk about precision leveling or precise leveling in terms of what the NGS does, because what they do involves very sophisticated and expensive equipment. So rather than focus on that, we're going to talk about how to make our own leveling practices be more precise. So let's talk about something called, actually, and this shouldn't say profile leveling. This just says should be precision leveling. Profile leveling is next, so just ignore that. So some methods to increase precision involve something called shading. Well, first of all, we already talked about some of these in the past, where we talked about setting the tripod legs firmly in solid ground, allowing the least amount of time between your backside and your foreside readings, having very well delimited turning points, very well determined turning points, limiting sight distances to 300 feet or less, avoiding leveling during strong winds or when the temperatures are very high, etc. So on top of that, this section in the book goes through some of the other ones that are interesting, but we're gonna practice some of these in lab, but not necessarily, or maybe you already have, but not necessarily look into these too closely. Some of these are shading the level. So shading the level involves keeping the level out of direct sunlight, etc. Also, three-wire leveling. So the three wires are another name for the stadia hairs or your crosshairs in your like the telescope. So whenever you're looking, it's a good idea to use all three horizontal hairs so that you read them and average them, and it helps you take the correct reading. Now, precise leveling rods are, again, just rods that are less susceptible to expansion and other things. Plus, it's just good form to not, again, to not leave them out in the sun, to not use them when they're like soaking wet. Those kinds of things are all fantastic. So it's fantastic ways of increasing the precision. And double rotted lines. So double rotted lines is when you use two level rods and set two turning points, two backsides, two foresides, so that then you can do averages. So anyway, if you're interested in this, or depending on what you're doing, rather than do it this way, you may just want to use more precise equipment like total station or whatnot. But using an automatic level is good enough as long as you use good forms and do proper practices. So now it's when we're going to talk about profile leveling. So profile leveling is something that is for the purpose of location, design, and construction. We must determine the elevation along a continuous path, such as highways, canals, railroads, water lines, etc. So profile leveling is a process of determining the series of elevations along that fixed line. And we're not going to look too far into this, but know that the purpose of this is to provide the necessary information to plot the elevation of the ground along the proposed route. So a profile is kind of, it's graphing different points at different elevations. If you do, like here my y-axis is the elevation in feet, and my x-axis is stations, which are equally spaced. So let's say that I'm checking a station every 50 feet, and I check the different elevations. So this looks kind of wonky, but in reality, you could be trying to build a highway that crosses through a very mountainous area, and you have like spikes and valleys and whatnot, and you want to figure out what grade you want to make your road be in. So you have to be smart about it, because if you make it, let's say, too steep, then you're going to have to build all this support and just go, if you want to go way on this little bump right here, if you go over it, that's great and all, but then that means that for a long time you'll just have to like fill in a lot of space. Now if it's too flat, that means that you have to carve out a ton of the terrain, which is also expensive, complicated, and potentially dangerous. So you see how here it kind of, this line sort of minimizes the amount of stuff, the amount of filling in and chopping out. So that's something very interesting that you could be doing, an application of plane surveying And there's cross sections. Cross sections are lines of levels or short profiles made perpendicular to the center line of a project. And it just helps to estimate quantities of earthwork. So they're great for route projects and burrow pits. Now this is just for your information. So let's say that we have terrain that's very uniform slope, then you just have to have a certain number of points with 3 rod readings are sufficient. If you have some interesting changes in the slope, you might want to consider 5 slope readings. Whereas if there's a considerable change in the slope, this one has 9 right here to make sure that this is kind of like a connect the dots game where you're trying to find the places where your slope changes. So between here and here, there wasn't much of a change, so you could spread them out. But between here and here, there was a big one, and here. So another application of plane surveying. Let's talk about slope and grade for a second. We've talked about this before, but this is just to let you know that sometimes slope and grade, although they represent the same thing, they look different. So the grade, as we've said, is like a 1.5% grade means a vertical change of 1.5 feet for every horizontal 100 feet. So in other words, it's rise over run times 100%. However, many times slope, so the grade is a kind of slope, it's represented as a ratio. So the slope is going to be equal to run, this sign for your ratio, rise, where rise is 1, so it's a unit ratio. So for example, a grade of 2% has a slope of 50 over 1. So you might be thinking, how? I don't get that. Well, okay, so a grade of 2% looks like this. Let's say we have a triangle and it has a, 2% is not very high. So let's say these are 100 feet right here. This is obviously not to scale. And this is 2 feet right here. So we can figure out that slope is equal to run, so 100 over rise, 2. And we can simplify those numbers, so that's where my 50 over 1. This is the same as like 100 over 2, and then you just go, well, this is 50 over 1. But you might see this, so this is the only reason this is kind of mentioned here. So let's do one brief example. It says the station at the beginning point of a highway is 15350. Now, you may see this notation. I'm not sure if we've mentioned this before, but when you see this notation, ignore the plus sign. What it means is that the original place, like the original quantity where we started doing stations, so you have like this, and then you have stations every so often. Let's say that this is 15300, and this is going to be 15350, which is written as 153 plus 50. And this is 15400, which will also look like this. Or you can do them every 25. You can do it various different ways. So just know that this is 15,350 or 16,225. So let's read this example. It says, the station at the beginning point of a highway is 15350 or 15,350. If the change in elevation to the end of the construction is at this point, 162.25, is 42 feet. What is the average grade and slope over this distance? So what this is telling me is the following. I have something like this, where this point right here is 15350, and this point right here is 16225. Yes. So the total distance from here to here is, I should have it somewhere. Or not, I can just, yes, I have it. I knew I had it. It's 875, and it said that over here, the difference in elevation is now up to 42 feet. No, yes, 42 feet. So what is the average grade and slope? So for the grade, what I'm going to do is to figure out, well, actually, no, I'm not going to figure out that angle. Grade is equal to rise over run over 100. Times 100%. So this is equal to 42 divided by 875 times 100%, and this gives me approximately 4.8%. That's great. Now slope, on the other hand, is 875, 42, which I can simplify which I haven't done. Let's see, I'll do my calculator for this one for sure. Let's see, 875 divided by 42. And it might not give you an even number, so depending on, here we don't have any decimals, so I'm just going to round it to the nearest one. Oops, nope. Okay, this is 21 to 1, approximately. But that's how a slope looks. Awesome. All right, and that's it. That's it for this lecture.